Alright, hello, and this is my fifth and final video for this physics project of the articles, and this article is titled, "This is how a fuzzy universe may have looked like." This article has a lot to do with dark matter's properties, and how that might have changed the formation of the universe. So, dark matter is theorized to be the starting ingredient for the universe's early galaxies, and dark matter, although widely accepted to be a major driving force of the universe's structure, none has ever been detected before. Other than gravitational effects, dark matter seems to have no interaction with ordinary matter. This gravity, however, helped draw normal matter into clumps, forming galaxies at the start of the universe. For the first time, scientists have been able to model the formation of the universe in three different scenarios. And these three different scenarios would be if dark matter is cold, warm, or fuzzy. So these three different sort of terms, cold, warm, and fuzzy, have to do with the makeup of dark matter. And since no one has ever detected, seen, or recorded any dark matter is really up for the win to whoever can make the best fitting theory for what dark matter may act like, be like, or look like when in motion and causing gravity. So cold dark matter here is the oldest theory, and it is the most widely accepted theory of dark matter. And it is that dark matter is made of relatively large particles, invisible and undetectable, of course, and it moves, and it is relatively slow moving as well. It is about slow moving, and it is also about 105 times the size of an electron. So that is the oldest and most accepted theory of dark matter, that dark matter is cold. So the second oldest and slightly more recent and slightly less accepted but still very widely known is the theory of warm dark matter. Warm dark matter is slightly newer, and it sees dark matter as slightly smaller, lighter, and faster particles rather than cold dark matter. So it's just slightly smaller, lighter, and faster particles. And lastly would be fuzzy dark matter. It is the newest theory, and it is a theory that dark matter is made up of extremely small particles, like ridiculously small particles. And it's about each particle is about 1/octillionth the mass of an electron. And due to their sheer minuscule size, they move and act like a quantum function wave rather than as a particle. Which makes fuzzy dark matter one of the odder of the three theories. So, if dark matter is cold, just as the oldest theories suggest, then galaxies, when they were first created, should be clumped together in parts such as this. I'm going to use blue to denote cold. They'd have one, that's not blue, they'd have one central halo of matter in which most of the dark matter was concentrated in. The dark matter is slow moving due to being cold, and it is all concentrated in this one area. And then outside of it would be smaller, less dense halos that of dark matter, or not dark matter, of just regular matter, in which these halos are waves of matter that are traveling towards the relatively stagnant dark matter in the middle. And then these halos will just repeat themselves on and around until it essentially pitters out. And so on. Now, with warm dark matter, things start to get a little interesting. I'm going to denote warm dark matter using red. And with warm dark matter, it does form a semi-central clump of matter, but warm dark matter also forms a few spindly thread-like little outcroppings or juts out of matter as the galaxy is formed. So this is most likely due to the fact that because warm dark matter is lighter than cold dark matter and that it moves quicker, the galaxy has time to extend its spindly arms a little further out, creating sort of like the thread-like arms of warm dark matter. Sort of completing up the picture here. There we go. And then last but not least would go fuzzy dark matter, the oddest of them all. So fuzzy dark matter in these simulations would look similar to, closer to warm dark matter than cold dark matter, but it is still very different. The central point of fuzzy dark matter is not well defined. There's little of a central point, but it also holds thread-like spindly protrusions like warm dark matter does. However, these spindly protrusions seem to come in sort of very consistent patterns of density, just as a wave would. So these harp-like patterns and spindles of matter is what a galaxy that is created using fuzzy dark matter would look like, which is rather odd. Scientists have been able to put together simulations of warm and cold dark matter before, but not of fuzzy dark matter due to limitations of the computer, because fuzzy dark matter incorporates basically the equivalent of a quantum function for every wave of dark matter that comes through, which is odd for the classical physical universe. So, in order to do in order to get this special fuzzy dark matter simulation, scientists need to use two special equations in order to get this. And those equations could be called, let's see, check through my notes, would be the Schrodinger's equation, which is the equation that all quantum waves need to follow. And this is used to simulate this sort of wave-like movement of the fuzzy dark matter within this galaxy. And then the second one would be Poisson's equation. And here, Poisson's is an equation that describes how the waves of dark matter generate density, and thus gravity, attracting matter to itself. So, Schrodinger's equation sort of shows how the waves pull density towards each other. So as these waves, like sound waves, they are more dense, where there's more matter here, just like regular dark matter. Or sorry, regular matter, it's more dense in waves. And then Poisson's equation is used to calculate the density at each of these waves when all these waves seem to like synchronize together in these areas here, which is interesting. So what this can be used for is, in the future we have a basic general understanding of what the galaxies may look like, depending on what dark matter, what theory of dark matter ends up truly being correct. So scientists are eager to get hold of telescopes in order to point them at the oldest galaxies we know, now that we have much more recent technology in both computing to create these simulations and in telescope technology. So in order that we can see these very far away early universe galaxies. But that essentially is that is the article. And in terms of questions that I have, what I'm really curious about is how this fuzzy dark matter moves in a behavior like a quantum wave, because I know that dark matter has no mass, it has no, I guess, velocity, it has no density, it has no anything else other than gravity to interact with the physical world, so it may not, the physical properties may not apply to it when the quantum equations are applied to it. But how does dark matter act like a quantum wave? It's particles, not a wave. So how can it be superposed all over the place if it's waves and not, if it's particles and not waves? That was the largest question I had there. And then secondly, if can we not look at other galaxies near us to see if dark matter is either truly fuzzy, warm, or cold? Because dark matter seems to be, as it says in the article, dark matter is relatively consistent across the universe with just a few blips here and there, like with waves or density patterns here or there. So could we not look at a much newer universe and extrapolate the same information, because dark matter is still being used to track that galaxy, is it not? So that would be it for my questions here on dark matter, fuzzy dark matter, and this article. So thank you, and that should be it for me.